Hello everyone. I've been looking for another game to use my 12-button controller with, and I thought I'd try and find one in my old Atari video game catalog. This was published back in 1981, back when the Warner Brothers company owned Atari. Let's take a look at what's inside here. There's quite a bit of artwork and classic game history that might be interesting for some. So this magazine or little booklet is organized into categories for each of the games. There's a skill gallery, a sports arena, a racetrack, and so forth. And it here has a picture of Pac-Man eating bubblegum or something to that effect. It's kind of odd. But we can go through this, and I've always liked the artwork for these cartridges and how they're depicted in the larger scale inside this magazine. This is from Asteroids. But anyhow, we can go through this and we can see all this stuff for the old games and their descriptions, and it's quite interesting to read. But what I'm interested in is at the back of this catalog. In the back, we have a list of all the games that are in this catalog and which controllers you need to play those games. This is so you don't go out and buy something like backgammon and then realize you needed the paddles to play it. I mean, that would kind of suck if you didn't know that up front. So nice of Atari to have put this in a catalog for your reference. But as I was scanning through this, something caught my eye. And that's right down here. It's this cartridge called Basic Programming. Basic Programming. Now, I have a background in computer science and mathematics, and I learned basic programming on my first set of Commodore computers. And that's a vastly different system from what we have here. How could we use this thing to write basic programs for this thing? And furthermore, what exactly would we be programming? Would it be a game? Would it be a cartridge? What is the usability of this thing compared to a keyboard? I had so many different questions, so I figured I might as well just buy the cartridge and explore what this thing can do. Let's take a quick look at the cartridge label. So this is Basic Programming, and it comes to us from 1978 by the Atari Corporation. And in fact, the programmer of this cartridge is a person by the name of Warren Robinett, who is famous for the Adventure cartridge as well. And Mr. Kevin Bunch of the Atari Archive channel spoke with Mr. Robinett and got some information to produce a brief documentary on the making of Basic Programming. Head over to that channel, which I'll link below if you want to learn more about the history of this cartridge. Now, there's also some internet lore or a rumor on the construction of this cartridge, specifically why Atari produced it. And to understand that, we have to look back to what the Atari 2600 was called before it was known as the Atari 2600. If we look on the catalog that I showed earlier, you'll see that the console is referred to the Video Computer System, not the Atari 2600. Now, think back to 1978. What kind of computers did we have around then? Well, we had the Commodore PET, we had the Tandy TRS-80, and we had the Apple II. And all of those had a basic programming interface and a keyboard that you can interact with. So if you bought this thing and it was called a computer system in 1978, then you might be wondering, how do I program it like my friend's PET or my friend's Apple? Well, in order to address those questions and complaints from customers, the speculation is that Atari produced this cartridge to justify the name of the video computer system that we see in the publications. Now, we're also going to need a pair of keyboard controllers, and this is what they look like. Two keyboard controllers are used, one in each joystick port, and an overlay covers the button pad showing the key mappings for this cartridge. A grooved edge on the side of a controller allows it to be physically connected with another, creating a tiny 24-button keyboard. Now, you might wonder how only 24 buttons can be used for programming, given that we have 26 letters in the English alphabet, 10 digits, several math operations, etc., etc. I'll explain that once we start writing programs. But for now, I'll say that this problem is solved with the button that's encircled by 4 arrows. Now take a close look at that button. Does the pattern seem familiar? Check this out. It is on the uniform of the operators that are depicted on the cartridge label. That is so strange. I guess that's how Atari imagined identifying programmers in the distant space-era future, by a logo on their uniform. Weird. Okay, I have one controller, but I'm going to need two to use this cartridge. Well, fortunately, I built a second one to go along with the one I built a few months ago. If you're interested in seeing how I built these controllers, I'll link to another video as well. It's a little long, but I suggest you skip the technical details and some of the mistakes I made while constructing this, and those links are listed in the timecode index of the description of the video, which I'll link to as well. And finally, we need an overlay that goes on top of these controllers. When I built these controllers, I intentionally skipped over the fact that I would need the overlays. I figured I'd just be able to memorize the controls for whatever game I played, but this is a little bit more complicated. It requires a lot more interaction with these buttons, and so I have a little cheat sheet here that I produced that shows all the different controls and the modes I need to put things into to get these characters and keywords to show up. More on this later. Alright, with that said, let's get all of this stuff hooked up and let's try to write some basic programs with basic programming. This is the setup we'll use for demoing this cartridge and writing some basic programs. I have my cheat sheet taped to the console for quick reference. And a quick note on this cheat sheet, what we're seeing is the inputs that are divided for the left and right controllers, and they're grouped by colors. The way we switch to a different color is by pressing the mode button, which is this one right over here. Every time you press this button, you cycle from white to red, red to blue, blue to green, and then green back to white. And in doing so, you're effectively remapping what all the buttons on these keyboard controllers will do when you press them. Alright, let's turn the system on. And this is what basic programming looks like when you first turn it on. Now you might notice that the text quality is rather poor, and this is sort of intentional based on how this cartridge is designed. Basic programming, at least my version, operates in NTSC video mode, which is 60 frames per second or 60 hertz, but my video capture system is only capturing at 30 frames per second, so half of the image that's being produced by this cartridge. Now, there are some clever programming techniques in this cartridge to optimize on the amount of CPU that's being used for rendering a video signal, and consequently, this cartridge is only rendering half of the video signal on half of those 60 hertz, and the other half on the other 60 hertz. So it's alternating between two images very quickly to produce a particular text pattern on the screen. And the consequence of that is that my capture system is only picking up one of those two images. So this is what it looks like. Now this is intentional. It's supposed to look like this. So if you see any other images that look super clear on the internet, I can assure you those are coming from one of the more popular emulators. So the screen is laid out into 6 sections, only some of which are viewable right now. The first section is the status section, and I can turn it on and off by pressing the first button on the left keypad in white mode, like so. The status section basically represents the amount of memory that's available to your program and the speed at which it's running at. The next section is the program section, pretty self-explanatory. This is where your program listing will be. And the third section is the stack, not to be confused with the call stack. This is actually an expression evaluation stack. So a good way to think about this is how a calculator handles arithmetic operations like 1 plus 2 plus 3. First, it has to do 1 plus 2, turn that into the value 3, and then it puts 3 on the stack and it adds it with the rest of the expression, which is another plus 3. So it'll do 3 plus 3 is 6. And in fact, we can see basic programming's implementation go through that evaluation of expressions in the stack section of the screen. More on that later. The fourth section is a list of variables and their values that are currently in the program. The output section is the program output, mainly print statements. And then finally, we have a graphics section, which is not shown on the screen, but if I turn off some of the other sections, then we can see it. So the graphics section is basically 2 blocks, a red one and a white one. The red one is currently on top of the white one. And in traditional Atari fashion, this is the extent of the graphics that you have available to you in this cartridge. You can move them around, and there's some limited hit detection that you can do when the two blocks are overlapping. So another nifty feature is that, let me just turn everything back on, is I can control these headings that you see by alternating the A-B switch for the left controller input. So I can get rid of all the headings for the sections if I was interested in doing so, or I can put them all back on. Personally, I like to operate in this mode because screen real estate in this cartridge is highly sought out for. But for our first programs, we'll keep things like so we understand what's going on. Okay, and before we start, let's set some quick expectations. So first of all, this is not a robust programming environment in the modern sense. Variables are limited to only one character. We don't have access to subroutines. We don't have access to memory operations like peek and poke. We don't have an input statement, so we can't read strings from the environment. But we can read key presses, and only single key presses from the second keypad that's hooked up to the system. And it's limited to just this keypad. You can't plug in a joystick and try and read inputs from that. We don't have access to several Boolean operations like AND and OR and NOT, though you can simulate AND with some if statement logic. Basically, these are the only Boolean operations you have. Equality, less than, or greater than, and less than. The numbers that you have access to, or integer variables, they're only limited to values between 0 and 99. And furthermore, you only get 9 lines of code to enter a program. You can combine statements on a single line pretty much for all operations, though print has some weird semantics that we'll just ignore for now. Okay, let's address the elephant in the room, which is the amount of memory that this machine has available to it, and consequently, the amount of memory that basic programming has available for you. There are 128 bytes of system memory available to the Atari 2600. That's bytes with a capital B, not megabytes, gigabytes, or any other unit. And half of those are reserved for whatever basic programming needs to execute its instruction code, store data in memory, and so forth. The other 64 bytes are what you get to do whatever you need with your program, and that's reflected on the screen. You'll see that it says symbols available 63. It's not 64 because the 1 in the program for the line number is consuming 1 byte of memory. So let's demonstrate what the implications are of having screen output and low memory available to you for a very simple program. This is going to be the program that everyone's probably written at some point in time when starting with BASIC, and that's the 10 print hello, 20 go to 10 style of program. So we'll do print. Oops. And finally, go to 1. Okay. And to demonstrate this, I will turn off the stack. And we'll turn off the variables since there aren't any, and we'll turn off the graphics since there isn't any. And let's run this and see what happens. And the program has stopped. Now, to demonstrate that there is more text output, I'll just temporarily disable the program section and the status section, and we can see that we printed hello a number of times on the screen, but the program has stopped. And why has it stopped? Well, the number of symbols remaining is 1, which means there's only 1 byte of memory left to execute something or to print something. And what we're demonstrating is that every time you print something to the screen, you are still consuming memory, even if that stuff is not visible on the screen or if it's wrapped up to the top of the screen. All of that is still stored in some special screen memory within basic programming, and therefore it goes against your 64 bytes. So to illustrate that point further, I can make a very simple modification to this program. First, I'll press reset to reset the data memory of my program. And that will restore a bunch of symbols or a bunch of RAM available to me, but it will keep my program intact. And what I'll do next is I'll insert a clear statement after the hello statement, and that will clear the screen every time that instruction executes. And we should now see this program run indefinitely or run forever. And as I'm typing things out, you'll also notice that every time I enter a token or a symbol into my program, that also goes against my memory count. So we have to be efficient with the types of programs that we're writing and not introduce too many unnecessary symbols. Okay, there we go. So once again, I will disable the program section while this runs. And when I run it, we should watch the memory count and see that it stays pretty much constant. And there you have it. So it's kind of cheating. It's printing hello on one line and it's clearing the screen and then it's repeating that indefinitely. But you can see that this will run forever. I can speed up the program execution using the faster command, and consequently I can slow it down using the slower command. So to do that, let me turn on the program section to see what color my cursor is. And it's white, so that's fine. And I will go make it go faster. And this is as fast as it will go. 60 is the largest speed. And I can also slow things down all the way down to a really slow speed where you can see every instruction being executed one at a time. Okay. I'll bring the speed back up again. Oops. Get rid of graphics. And we're done with that. So let's halt the program and let's reset to clear our memory. Let's take a closer look at how memory is consumed inside basic programming. And I'll do that with another program. So first, to erase my program, I can press select. This will clear the program state and also the memory state of the program. So it's effectively going from a clean slate, contrary to reset, which only removes the data that's been used by your program. This next program will show how memory is managed and allocated while a program is executing. And I'm going to type it out in real time so you can see how cumbersome it can be to use these two controllers when you're not that familiar with them. It's a short 4-line program, and I'll describe what it does as soon as I'm finished entering it. Okay, done. So that took a little bit of time. If I had a keyboard, I could probably have whipped that up in a matter of seconds as opposed to minutes. So what we're doing here is we're tracking the state of 3 variables, A, B, and C. And on line 2, if A is even, that's the mod 2 operation, then we're going to increment the value of B. And then on the following line, if B is divisible by 3, so if mod 3 is equal to 0, then we'll increment the value of C. And then we'll go back to 1, and then we'll continue to do all the necessary checks accordingly. So A will constantly be increasing by 1, and B will increase by 1 when A is even, and C will increase by 1 when B is divisible by 3. So let's take a look at what happens when this program runs. I am going to enable the stack. Oops, I'm in the wrong mode. Erase. Okay, show the stack, and we'll show the variable section and the status section, and I'll turn the program off because that's not important for this demonstration. Status and variables. Okay, so the first thing to remember is that this program is not explicitly outputting anything to the screen. There's no print statement. We're just incrementing values of variables. So keep an eye on the stack and keep an eye on the variables, and you'll see what gets printed there at certain times. And then also keep an eye on the symbols. I'm going to run through this program one instruction at a time by using the step operation, and therefore we can see what's happening at each moment the program counter is incremented by 1 statement. So to start off, we get a value of A. So you'll notice A is assigned the value of A, which is 0, plus 1, and 0 plus 1 is 1. And there it goes. A has been given the value of 1 in the variables. Now, did you see what happened in the symbols as the program was executing those statements? So let's take a look at that again. The next statement is going to be an if statement. So if is being printed to the stack, and every time something is printed to the stack, we'll notice that the symbol count goes down, which kind of goes along with what happened when we printed something to the screen. Every time something is printed to the screen, we lose memory. But the nice thing about the stack is that it expands and it contracts as expressions are collapsed into simpler values. So 0 mod 3, that's going to be 0. See, we get some memory back at that point once that statement ran. 0 equals 0, that's true. So that gets collapsed to the truth value of 1. Now we're going to assign a value to C. So C is assigned the value of C, which is 0, plus 1, which is 1. And now watch what happens next. We have 22 symbols right now. Oh, but now we've paid 4 just to track the value of C. And we go back to 1 and return. So this is somewhat annoying that if I want to track the state of the variables, which is out of my control, I got to pay for that in terms of the amount of memory that's being allocated from the space in my program. Now you might ask, what happens if I hide the variables section? Will I get that memory back? Well, let's find out. Push variables. No, that is constant. What about the stack? Do we pay for the stack if we're not seeing it on the screen? Yes, unfortunately we do. So I'll run this program one more time with those sections disabled, and we'll see that we kind of hover around 15, 14 symbol usage, even though those sections are not displayed on the screen. So I'll press reset to reset the state of the program. And that returns back all available memory, excluding what the program is using. And then I'll hide the variable section, and I'll just run the program and let it go, and we'll watch what happens to symbols. And you can see that it's kind of hovering around that 14, 15 mark. I'll slow it down so we can see it a little bit more clearly. And nothing is being printed to the screen, but we're losing memory as the program executes. So that is the most important thing to keep in mind when writing basic programs, is the amount of memory that's being allocated. And if you understand how the memory is being allocated, in terms of what gets stored in the variable section or what gets stored in the stack section, then you can tweak your program accordingly to expect that or to take advantage of that. Hey, thanks for watching through to the end of the video. This concludes part 1 of an overview of basic programming for the Atari 2600. In part 2, we'll take a look at the other language features including music, keypad inputs, and graphics. We'll also do some real-world code optimizing, so be sure to keep an eye out for the conclusion. Please consider subscribing to support the channel and using the like, dislike, and commenting features to provide your feedback. Hope to see you back soon.